Today we shall deal about oscillation due to a spring. The simplest observable example of simple harmonic motion is the smallest oscillations of a block of mass m fixed to a spring, which in turn is fixed to a rigid bar as shown in figure 1. In figure 1, a linear simple harmonic oscillator consisting of a block of mass m attached to a spring. The block moves over a frictionless surface. Once pulled to the side and released, it is used simple harmonic motion. It means to say the spring block functions as a simple harmonic motion in to and fro conditions. The block is placed on a frictionless horizontal surface. If the block is pulled on one side, if the block is pulled on one side and is released, if there is huge to and fro motion above a main position, let x equal 0 indicate the position of the center of the block when the spring is in equilibrium. The position marked as minus A and plus A indicate the maximum displacement to the left and right of the mean position. We have already learned that the springs have a special property which were first discovered by the English physicist Robert Hooke. He had shown that such a system, when deformed, is subject to a restoring force, the magnitude of which is proportional to the deformation or the displacement and acts in the opposite direction. This is known as Hooke's law. It holds good for displacement small in comparison to the length of a spring. At any time t, if the displacement of the block from its main position is x, the restoring force F acting on the block is F power minus k. Thus, the constant of proportionality K is called the spring constant. Its value is governed by the elastic properties of the spring. A stiff spring has large K and a soft spring has a small K. The equation 1 is same as the force law for SHM, and therefore the system includes simple harmonic motion. We know that K barabar m omega square. So omega barabar root over k by n. That is equation number 2. And t, the time period of the oscillator, is given by t barabar 2 pi root over m by k. Thus, we observe that from equation 1 and 2 and 3 that a large angular frequency and hence a small period is associated with a stiff spring. It means the value of K should be high and the block should be light or a small m. Therefore, for a small time period, the spring must be stiff. It means the value of K should be high and the mass of the block should be small. For a small time period in the simple harmonic motion acting by a spring,